Alright, silly people, here's the situation. We're going to try to prove that for any matrix T with arbitrary elements, they all have the property that the determinant is just equal to all of the eigenvalues multiplied together, and then the trace of it is going to be equal to all the eigenvalues added up. So, um, the way to do this is to first set up the characteristic equation, which we know will solve for the values of lambda 1, lambda 2, lambda, so on. That being that the determinant of T minus lambda times the identity matrix will be 0. So for us, that's the determinant of T11 minus lambda T21 dot 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 Tn1 T12 T22 minus lambda dot 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 Tn2 dot 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 here to T1n dot 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 here to T2n dot 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 diagonal dot dot dot. It gives you a T n n, and it's Tnn minus lambda for the last term there. But yeah, you take the determinant of that, you get 0. Obviously it's impossible because there's n unknown elements. But we know the solution to this. We know that there are going to be eigenvalue solutions to each of these, so we can actually write it as lambda 1 minus lambda 0 dot 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 0. Point is that all we have are the diagonal components, right? And then you have a lambda n minus lambda down here. And the determinant of that is equal to 0. So we can just multiply the diagonal elements together. Dot 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 lambda n minus lambda. And we can expand this polynomial because we're going to have minus lambda to the n, right? So we have minus lambda to the n, plus we have all of the lambda to the n minus 1 terms. So you take lambda, multiply it by n minus 1, and then you're left with just the lambda 1 plus lambda 2 plus lambda 3 after you factor that out. So it's lambda 1 plus lambda 2 plus lambda 3 dot 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 lambda n. Yeah, that's what's left over from that. And then you get a bunch of intermediate terms, which we don't care about. But then we do have the lambda to the 0 terms, which actually just end up being all of the eigenvalue solutions multiplied together, right? So that's how you would write that characteristic equation. Obviously, it's pretty vague because there's all of these terms, but we don't care about those. And so what we do is we compare this to the general characteristic equation, that is Cn times lambda to the n, Cn minus 1, lambda to the n minus 1, and then all the stuff in between, and then C0 lambda 0 equals 0. And so we see that C sub n is just minus 1 to the n. We see that C sub n minus 1 equals minus 1 to the n minus 1 times lambda 1 plus lambda 2 plus lambda plus a bunch of terms on it to lambda n. And we know from theory from the last problem that C sub n minus 1 is always minus 1 to the n minus 1 times the trace of whatever matrix you're doing. So knowing that, we can cancel out the minus 1 terms on either side and say we can see that lambda 1 plus lambda 2 plus dot 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 plus lambda n is actually just equal to the trace of t. So we did prove that. Um, Finally, we can observe that C0 is lambda 1, lambda 2, dot, 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 lambda n. And then in theory, we know that that is equal to the determinant of whatever matrix you're trying to get the eigenvalues for. We know that from the last problem as well. But then that just completes the proof then. That, yeah, for any matrix, the solutions to the characteristic equation constitute the trace and the determinant. All right.